is a little bit close. All right, let's jump back in. I think we left off here, right? Yesterday, 135, 136. 136. Go ahead, take a turn. 136. And let's see if we can work through these three. Okay, 10, 11, and 12. Let's do the first one together, just to make sure we're good. Now, I'll let you loose on 11 and 12. And obviously we need to know what directions we've got. I just said find the derivative. Is this ready to go for the derivative yet? Not yet, not for us. So we're going to have to rewrite the function first. We're going to rewrite that function first. How do we do that with these rationals? How do we get rid of the whole fraction part of this? I would just make the denominator x to the 6. I know what you're thinking of, like trying to create something useful. I like it. Yeah. Okay. And so, what do you mean by that? Okay, and then, like, do we just do it for the first one, or all of them? Right? Every single term is being divided by x to the third. Like, here's, you don't have to write this part, but here's what you should be thinking: is that everything is over x to the third. And subtracting exponents is a great way to do that. So when we rewrite this function, still h of x here, minus 1, right, plus 2x to the negative second, minus 2x to the negative. There we go. That's h of x. That was. Okay, now here comes h. And sometimes we don't have to do all of that like prep work ahead of time. If it's written the way we like, then we just jump into it. But if we have to do some rearranging, that's the best way to deal with those rational functions that just have one term on the bottom. If that was x squared minus 1, we'd be in trouble. And we need chapter 3 for that. Right? But let's do it. Quick power rule, hopefully, from yesterday, we're good to go. Drop the exponent in front, multiply through by the constant, decrease the power by 1. Drop the exponent in front, multiply through by whatever constant's there, decrease the exponent by 1. Could you imagine doing that with limits? X plus h squared plus 2x plus h minus 2 all over x plus h cubed. And then minus the original function all over h. You have to expand and factor. Oh my goodness, such a mess. This is so nice. Do we like the way that looks in blue right now? What's bothering us about that? Okay, and so let's just make this back, right? Just like we did in red, let's go this way. H prime of x equals negative 1 over x, right? Coefficient stays on top. I like to put the sign out in front. Minus 4 over x to the third plus 6 over x. Hopefully that switch, you're like, oh yeah. But if it doesn't, like, as much as I keep saying it, it's still so true. You can't just sit there if you have questions. This is such a dialogue, conversation kind of class. If you have a question, probably somebody else does. And we want to ask those early and often. Plus, this is more fun. Do we like that? Is that good? I like it. And I'm happy to stop right there. Now, like I've said a few times, there is the possibility that they might make you do this. Right? One single rational function all over a common denominator. The nice part about monomial denominators is it's very easy to make them. You just have to multiply by however many x's you're missing. Oh, I'm missing 2x's here, so negative x squared. I'm missing 1x here, so negative 4x. I don't miss any x's there, so we're good today. Okay. But red is good for me. On the test that I write for you, and that's going to be all of them this year. Probably have 2 of them, I would guess. We'll probably have one for chapter 2 and one for chapter 3. Oh my goodness. I'll never make you do that step, but it is good to practice. Cool. Sweet. You try. Go for it. Try 11 and 12. See if you can do it. And I'll tell you right now, we have some rearranging, some rewriting to do for both of them. Well, I'll let you try them first. If you get stuck, ask questions. Or take a peek. I'll rewrite the functions, and then I'll let you get after. Power over roots. But then we're not done. Got to get rid of the fraction. Power over. I want to make sure your functions are right. Take a peek now before you move on.
How did you get the 2/3? You just
Subtracted exponents. When we divide, just like we did on 10, we subtract the exponent straight down.
Yeah.
So this is 3x to the first, and that's x to the 1/3 because power over root. So, and when we divide variables at the same base, we subtract their exponents. So 1 minus 1/3. Yeah, so I took this number and then subtracted that from it, and that's going to be my exponent.
Thank you.
Ready? No rush. So take a couple minutes. You have to peek back at what the derivative of cosine is. Go for it. Just remember that the constant just gets multiplied through, so you don't have to worry about the -3 until you figure out what your derivative is. Just take that -3, multiply through. The other thing I hope you start recognizing is some of the notation that I think is worthwhile to use in kind of my setup. I worked through the function first. And I worked left through right. And if I needed more lines, I would have came down and did that. But with my derivative, I like to work down. But if I needed the space, I'd be happy to do it, typewriter style, just left to right, kind of work my way down. But the thing that I want you to start noticing is that as I work straight down like this, I don't keep writing f prime of x over and over. If I have line after line after line after line of work, I'm not going to keep rewriting the left-hand side until the end. That's pretty common. You say, okay, here's what I'm going to do. And you just kind of work through one side. But I could have gone this way. Or I could have definitely just, I could have done that. I don't have to work straight down. But eventually I get to a line where the answer is isolated. And I'll do it sometimes on like answer keys where my answer will be kind of like all the way to the right of a problem. And, it's not one single sentence, but with derivatives, I really like to try my best to say, okay, here it is. The derivative of f of x is this, like right next to each other, rather than all connected all the way across. But that's up to you. That's totally up to you. I just like the way this is. Calculus definitely has some style. Like you get to kind of pick your style. How do you like it? How do we do? Not bad? Is there any changes that we could make? Is there anything different that you did? Anything that you have questions about? Does yours pretty much look like that? Did anybody take 12 and make a single rational function out of it? Big, what'd you get?
I got 3 plus the 30x, 3 to the sine x, all over 3x.
3 plus 3 square root of x sine of x?
Yeah.
Cool. Perfect, right? Because all we have to do is multiply this one top and bottom by whatever that denominator is in there. I like that. Okay, so what's in blue? Like I said, I'm never going to make you do that. But sometimes, if you're thinking ahead, especially BC, AB is certainly easier than BC will be because you're going to see all this stuff again in the fall, which will be really nice. You'll feel like that fall semester should be pretty simple, I think. But that answer might be on a multiple choice on an AP exam and things, so we want to make sure we're good. Cool. All right, moving on to the page. I like it. When we get to page 137, I'm actually going to have us skip all the way down to the bottom. We're going to go to the last question on the bottom because this really starts getting us into what we want to start talking about. Question number 17. There are good questions before that, but I think it's too much of the same thing. Equation to tangent line, kind of all over and over again. I want to get to stuff that looks like this. And I know we did a little bit of this yesterday, talking about those spots where the function could have a horizontal tangent. Do you remember what we do when so this is not just, find the derivative. It's, okay, tell me the values of x, there they are, right? Where this function flattens out for just a brief moment in time. Could be a min or a max, maybe not. What should we do? Remember? This is calculus A. What's the first thing we're going to do? Thank you. Absolutely. First thing we're always going to do, let's find the derivative of this thing. And this one's a nice one. This is a nice, simple degree 4 polynomial already written the way that we want. Beautiful. There's going to be kind of 2 steps that we do. So go ahead and find the derivative of that quick one. Lainey, welcome back. What'd you get?
I got 4.
All right, because the derivative of 2 is a 0, so we don't have to worry about that one. X1 drops down, multiplies through, good to go. Nice. And if this was, page 136, yeah, it would be done. But now we're getting kind of towards the end of the chapter. We start putting these ideas together and using the derivative for some good. What do we want to do with that derivative to find all of the spots where this graph has a horizontal? Awesome. every time you see horizontal tangent, I am thinking that the derivative is, because that's the slope of my tangent. If this tangent line is perfectly flat, the slope is just 0. Now they could ask different questions. They could say, find all the values of x where the slope of the tangent line is 2. Okay, cool, I'll set it equal to 2, right? We can solve all kinds of different things depending on what we're looking for, but this is the most common one. Okay. Seriously, the calculus is done. Now it's just our skills in algebra that are going to come in. How do you solve this type of equation that has different powers of? If it was just x cubed, I would just go get it, right? I would just solve for x cubed and then take cubed. But I can't do that because we've got different powers. Wait a minute. Let's factor. And taking out the GCF is always a good place to start. 4x, yep. Take the constant that's as big as it can possibly be, which is going to be no bigger than the smallest. And then the smallest power of x, good. Okay, what do we have left? Ooh, I like that. Sometimes the GCF is not the only kind of factoring that we can do. All right, we pull out that GCF, and they like to do that. They like to stick a common factor in there, but then what's left is still factored. What kind of setup is that? X squared minus 4. That's a difference of 2 squares. Nice. And so whether you're looking for the difference of 2 squares, or maybe it's just quadratic, or maybe some indifference of perfect cubes, or whatever, we can kind of keep going. Right? 1, 2 factors there. X plus 2x minus 1. Oh. Okay, now what? How do we figure out all of these x values that are going to work? Yeah, look at each individual factor, right? And if you want to write this step out, set kind of like each one, okay, 4x goes equal to 0, and x plus 2 is equal to 0, and x minus 2 is equal to 0. You can show all of that work. I'm a big fan of it to get you to there. But the reality is that if you can see that ahead of time, I don't need what's in blue. Okay, if your algebra skills are good enough, you say, okay, I've got something factored. I've got this factor expression. It's equal to 0. I'm just going to figure out what makes them all 0. I recommend putting them in order from left to right. When you write them as a set at the end, if you're going to take that step that I just kind of wrote out, I would definitely write them in order from left to right. In terms of least to greatest, -2, 0, 2, rather than 0, -2. That's just good practice. Here we go. Determine the x values. There they are. Let's see how we do. Let's see if we actually got it right. Can I erase? Cool. There's that function. -2, 0. All the spots on this graph. And they actually ended up all being relative extrema too, which we didn't know ahead of time, but we knew for sure that they had those horizontal tangents. But all we got were the x values. How, if they asked us to, how would we figure out the y values? How do I figure out the -14s and the 0,2 or 2? Anna? Yeah, not the derivative, because what would we get if we plugged it into the derivative? And what would we get? We'd get 0 for all of those, right? So you don't want to plug it back into the derivative. We just use the derivative to get those answers. You want to plug it back into the original, that x to the 4th minus 8x squared. Cool, nice. And look, degree 4, so it's even, so the arrows are pointing up. Positive leading coefficient, right? Looks good. All right. Nice. Okay. We're cruising along today. You guys are fine. Let's go for 18. Now, this is another one that I want to do together just to be safe. I'll let you, like I said, I'll let you loose really, really soon, probably as early as tomorrow. I'm kind of doing some stuff on your own. But I want to look at 18 together. probably just because it's got some trig in there, and I just want to kind of get on the same page as to how we're going to deal with that. But it's the same question, right? Determine the values of theta, right? They're going to use theta because it's angles. They give us a function, square root of 3 times theta plus 2 cosine theta. Figure out what values are going to give us a horizontal tangent. Okay, so it's the exact same question. We're going to find the derivative instead of equal to 0. Thankfully, we only have to look in there. All right, we only have to look in the interval between 0 included and 2 pi x. All right, so we don't have to write both answers. We'll just write one if it comes up. But I guess the first question is f of theta ready to go? Is that function set up the way that we like, or do we have to make some adjustments? See some of this, I see some of this, I see some of this, I see some of, please don't look at me. You want to figure out if it's ready to go, just look turn by turn. Okay. We'll start with the simpler one. Is that piece ready? Sure. Constant times cosine. How about that? That's the one that's probably sending us off in two different directions. Yes, it's ready, or no, it's not. Anybody that's saying no, do you have a reason behind why? Like, what about that square root of 3 times theta is bothering you? Is it the square root? Me too. Like, that's the thing that I look at this and it initially bugs me. Well, all right, square roots, yuck. I know I have to make a change. If that square root has a variable on it, right? That's the thing that I care about, are variables to exponents that are fractions or negative or something like that. But take a look at where that square root starts and stops. Just the constant. I don't need to rewrite 3 to the 1/2 times theta. It's coefficient, variable, exponent. It's ready. So don't let the fact that there's a square root in there initially like force you to make the change, because this is the change you would make. What are you going to do with that, right? Nothing different, right? It's still just a number. So I think this is actually ready to go. I think we're good to go here. Let's jump in. Let's go for it. That's prime theta. But you might pause here and say, okay, well, what am I supposed to do? All right, well, maybe think of it like an x, if that helps. I don't suggest writing it out, because if you write your answer in terms of x, it will be wrong, and we don't want to do that. But maybe think of, don't even think about that. Like, think about just the derivative of 3x. What's the derivative of 3x? It's linear, the slope, right? 3. Okay. Well, if the derivative of 3x is 3, what's the derivative of radical 3? Okay. So that takes care of it. Kind of nasty, but it is what it is. Okay. All right. What about the plus 2 cosine theta? Well, remember, it's just a constant being multiplied through something that has a variable. So I can deal with the derivative of the cosine part, and I'll just make it 2 times 3. So what's the derivative of cosine? Negative sign, right? The derivative of cosine is negative sign. So what's the derivative of 2 cosine? Negative 2 cosine. Nice. So there we go. So minus 2 sine. There's my derivative. Now you can see why I want to try out. All right, we want horizontal tangents. So what should we say to do? Let's do it. So, square root of 3 minus 2 sine theta. Put the parentheses around the theta if you want. It's totally up to you. If that was like theta plus pi over 2 or something, if there was a phase shift, then we absolutely need it. But just theta or just 2 theta or 5 theta, we don't really need it. But it might help you realize that, that's what we're trying to solve for here. And that thing is buried within us. So I can't solve for it directly until I at least isolate sine of theta first. Let's try to do that. What should we do first to try to get sine of theta? If you divide by 2 now, you just have fractions everywhere, and that's okay. My suggestion would be, if you're going to do that first, if you're going to take care of division and multiplication first, that you do it individually rather than one big fraction on the left and one big fraction on the right. Now, we're going to get to the same spot in the same way. So, but I'm going to back us up because there might be a suggestion that helps you avoid fractions early. Obviously, we're going to have fractions later. But is there something we could do first so we don't have fractions right away? Move the square root of 3 over first with subtraction. Some people might like that option first so that they're avoiding having a bunch of fractions all over the place. And now we'll do it, right? We'll divide by -2 now. But the nice part about making that choice is instead of dividing by 2, now we're dividing by -2, and we're isolating sine from the beginning. That's a negative radical 3 sine. Because now we get to here. Parentheses if you like. Okay, isolated sine. And so what do you start, like I close my eyes and I start picturing something, or I take something out of my notebook and I start looking at something to help me figure this out if I don't know it. What are you envisioning us probably going to have to take a peek at? Yes, sir. Well, that wasn't bad. A little egg shape, but I'll take it. All right, sine, is that x or y? Y values. So we're looking for spots on the unit circle where the y value is radical 3 over 2. If you don't know those, that's okay. You're going to have to use the unit circle to get yourself. Now, calculator can help too, right? It's plug in the inverse sine of radical 3 over 2. Problem with that is it's only going to give you one of them. And unless it's quadrantal, you are guaranteed 2 spots for sine and cosine for all the angles in the quadrants themselves. So not 90s or 180s or 270s. The issue that we have is that the calculator is going to get us to there first. And it's going to stop. And if you're in degrees, it's going to tell you that you're at 60 degrees. If you're in radians, it's going to spit out the decimal version of pi over 3. And I'm never going to recognize that as being actually pi over 3. But there's another one. What's the other one? Yeah, there's another one. The problem is it's over here. And your calculator is never going to give you both of them. Right? It's only going to give you pi over 3. We're going to have to make that leap. So theta equals the set pi over 3. How much is that? That's how I would write that best if I was really getting all fancy and nice. There's your. All of your 1/2s are radical 3 over 2s. Those will happen at multiples of 30s and 60s, right? All of your radical 2 over 2s are all your 45s. But in my mind, if it's like, oh, radical 3 over 2, that's the big one. Okay, I'm looking for big y values. Let me go to the top of the unit circle, right? And pick the ones that are closest. Okay, good. Now you got a pretty good handle on it. Now, let's start putting some things together. I'm going to skip 19 completely. Let's turn to the next page, page 139. Yes, that's 20 minutes ago. Fine. All right, let's start to put some connections together. And there's still kind of one big thing that's left for us to do. And this table kind of alludes to it here for a second. But some of the things that we're trying to do is make connections between the function and the derivative in both directions, right? If the function is this, and the derivative does that, and vice versa. This is the vice versa part. If the derivative is, or changes, whatever, let's see if we can make some nice, true statements that kind of covers everything about the function at these spots. So if the derivative is 0, so like here's an x value or 2 or 3 or 4 or whatever, and you've got the derivative is going to be 0. What do we know for sure about the function at each of those spots? Make it nice, make it fancy. What do we know guaranteed? The derivative is and so what could we say that doesn't include the words like is not? Tell me something that's true, not something that isn't true. Okay. I like that. The tricky part about saying constant is we usually talk about like constant intervals, like there's a whole flat section of the graph. This could be instantaneous. It could be just one single x value or a collection of single x values. Oh, horizontal tangent line. There you go. Nice. So I think you're right. I think constant is a good word, but it's just a little misleading. I think then f of x has a horizontal tangent is a good way to say it that kind of connects what we've been doing. But Jacob, I gotta be honest, man, I actually like the way that you're saying that even better because you're talking about the function, like the function itself, not something I could draw on them. I think the more we start leaning in that direction, like talking about the behavior of the function and not the kind of stuff that we could draw on the function, I think that that's going to help. So I like the point of view there. I'm a big fan of picking out ways to say, okay, the function is doing this, function is doing that. Now here's the thing I could draw on. But yeah, it has a horizontal tangent. That's good too. All right, what about the second one? If the derivative is greater than 0. Now we're looking at maybe a spot, but maybe like a whole section, whole interval where we're getting positive numbers back from the group. What does that tell us about the behavior of the function? Not necessarily. Remember, it's behavior, like what the function is doing, not where it is necessarily. The derivative doesn't tell us a whole lot about where the function is. It tells us more about how the function is behaving. Anna? Good. And f of x is. And of course, we're always talking left to right. Graphs are always read from left to right. Beautiful. Okay, here's the easy one then. What if it's negative? Beautiful. And the thing that I want us to start remembering is that, sure, positive, increasing, negative, decreasing, but the size of those numbers tells you how fast that stuff is happening. The bigger the positive number, the faster it's increasing, the steeper that's going to be. And so a lot of this whole like rate of change kind of idea, like how fast things are moving, I think is going to help us too. Okay, cool. And all that stuff is all old news, but let's get a little bit more specific. What if the derivative at a certain point changes in the space nearby from positive to negative? Now, absolutely. There's only one way to go from increasing to decreasing. At a point, it has to be a maximum. F of x has a relative maximum. Like guaranteed. And that's so nice that there's nothing else I can do to go from increasing to decreasing without hitting a relative maximum. I just I do it with my hands. Boom, oh, there it is. Has to be, right? What if it goes the other way, from negative to positive? Like Evan did too. Evan's joining in. Minimum, absolutely, has a relative. And that's eventually kind of the end of this chapter. Is yeah, we're finding all of these spots where the derivative is 0. And of course, like that's like probably going to happen, right? If we're going to change from positive to negative and things are continuous, I better have a 0 in between there. We're just trying to figure out, is it a max, is it a min, or is it neither? Because it could be. Okay. Now the fun kind of takes a turn. And it gets a little bit more challenging when we try to do it graphically. Now, this graph on the left, this is f of x. They're giving us the graph of a function. And what they want us to try to do is come up with a graph for the derivative. Now, this is, and they said it, this is a possible graph. We are going to sketch this as best we can. We are probably going to be off by a little bit, but we're going to try our best. And I think the only thing that we can really do is kind of like stop at each one of these points and try to figure out what we think the derivative might be at that spot. Now, I don't know why I didn't scale this one out. 1, 2, 3, 4, 5, 6. -7 is that first. So at that x equals -7 spot, sure, the y value is -3. I don't really care about that. I care about what the derivative is at that point. My phone went off last year too. So, what do you think? What do you think the derivative might be at -7? Now, when you're trying to estimate derivative without an actual equation, you can't like plug in -7 anywhere. What are you envisioning? Why'd you say 2? Okay. So you're trying to like maybe draw a little tangent line. Now, see if you can draw something that only hits the graph once in the space nearby, but the thing that we want it to do, not just hit the graph once, we're trying to get a sense for how fast this point is moving right there. Like it's taking this trip along this function, right? But we are like stopping right here. And we're trying to think about what direction is the function pointing at that spot. And I don't care what analogy works for you, but for me, it's usually like here I am walking up and down this hill. If I was like perpendicular to the ground like I normally am, right? Where am I looking? Definitely looking up. But how far? And it's that steepness that we want to figure out. We all know it's increasing there. I know I'm going to put some positive number on there. What is it? 2, 3, 4, 5. You want to try, if you can, to draw a tangent line that points in the direction that the function is moving right at that moment. And that is easier said than done. And so the thing about a slope like 2, like actually like draw a line with a slope of 2 that goes through that point. I don't know that that's quite steep enough. That's me looking into the ground, right? If I'm walking along the side of the hill, I just don't know that 2 is big enough. I think it's got to be at least 2. What do you think? 4? If you say 4, try it. 1, 2, 3, 4, and over. That looks pretty good. It's probably about the direction I'm pointing out. I think anywhere like 4 or 5, I think would be good. The issue that I have with a number like 3 is there's another point on the function right at that spot, just a point away. And so it's pretty unlikely that 3 is big enough. I think 4 is pretty good. But I think 4 or 5, either one's good. Again, a lot of estimating here for sure. And so what do? Well, I go to -7 over here on this graph. What's the y value where this point's going to be then? We just said that the derivative at this spot, we think the slope of the tangent line there, let's say is 4. Let's all agree on that. Go to -7. Where should I go to put this point? Four. The y value on this graph here on the right, not the value of the function, it's the value of the derivative. That's best we can. -7, 4 is a point on the derivative. Again, looking at the derivative, we have no idea where the function is. No idea. What I do know is that it's increasing at a rate of about 4. Okay, let's go to the next one. -6, right there. What do you think? What do you think that? Trying to erase. What do you think that tangent line might look like? What do you think that slope might do? Yeah, I mean, and the best thing you can do is if you have a pencil, like kind of lightly, just gonna like draw a line that goes up 2/1 and hits that point. And ask yourself, does that look pretty good? It kind of feels like that's the direction things are pointing. And eventually, we'll in Calc B or C, I forget which one, you get into like sloped fields, and like there's like, oh, it's so cool. But it's just like a bunch of little tangent lines all drawn out there. I like that. So -6, there's a point right there. And what you see just between those 2 points is that as I'm moving from -7 to -6, it looks like the slope of my tangent lines are getting smaller, right? From -4 to from 4 to 2. What that means, and this is kind of the most important part of this, is that the rate at which this function is changing is starting to slow down. It's not going up like it's fast, right? Because derivative rate of change, for sure, is a good way to think about that. If I'm approaching 0, I'm not changing quite. Cool. What about at, so I skipped -5, so let's go to -4 there, right? Yeah. -4. What's the slope of that relative max up there? You know it. -4 is 0. That's an easy one. Now that we know, we see that relative min, relative max, right? That horizontal tangent line got it. All right, they skip -3, they go to -2. All right, what do you think? Slope of that tangent line. -1? Yeah, that's not bad. I think that's pretty good, right? Go like kind of down 1 over 1. I think -2 might be too much, but you know, maybe it's -1.5. Who knows? It doesn't have to be perfect, but let's stick with -1 for now. I like that. -2, -1. Now they skip 0. They keep skipping points, which is going to make sketching this graph a little bit trickier. The more points we have, the easier it is to sketch, of course. Okay, so they skip 0. Oh, did I put that up? Oh, did I forget one? Oh, I forgot this one. Yeah, -1. Oh, geez, like there's so many tangent lines that I can draw. Like all of these only hit the graph once. That can't be right. I need to, that's why the whole slope of the tangent line thing is good to start with. Really want to think about, okay, if I'm walking down this hill, if I'm skiing down this mountain, I'm pointing my skis straight down. I'm going pretty darn fast at that point. That's why snowboarding green. But maybe some nice big fast blues, but no blacks. But this looks a lot steeper, right? If I'm pointing down this hill, man, I'm going a lot faster than that -1. What do you think? -2, -3, -4, what do you think? -3, yeah. -2 just might be a problem because it would connect these 2 points right there. And that's not the worst thing in the world. It still could be tangents in the space nearby, because the space nearby, we didn't get into this in Calculus A, but there's this whole epsilon delta. There's a whole like proof thing of what limits and stuff and derivatives, saving us from the headache. I think -3 looks pretty good. Maybe -4. That might be a little too steep. Let's go -3. That sounds good. -1, -3. All right, now we're over here at 1. Relative min, easy. Skip another point, and they take us to 3. Go ahead, you try these 3. See if you can come up with your best estimate for what the derivative is at 3, 5, and 7. All right, this is x equals 3, this is x equals 5, and this is x equals. See if you can do whatever you. We're all going to be pretty close. And because we have that freedom, you're going to see that I can't be super picky about the difference between a slope of 3 versus a slope of 4. And I won't. Definitely. But I think what helps is trying to draw in some lightly colored tangent lines to give you a good sense of what it might be. Those are my best guesses. Might be off by 1 or 2, that's okay. Don't connect them just yet. I want to talk a little bit about what those connections might be. But I'll let you finish up. We're looking at your x7, hopefully by this point. But look at all those, the x-intercepts on the derivative turned out to be all of your relative extrema from your function. But only because it changes sign from one side to the other. Right? It went positive to negative at a 0. Oh, positive to negative, that's got to be a max. Negative to positive at a positive 1. Yeah, okay, went down and head back up. It's got to be a max. The question that I think we're kind of stuck with now is, well, if these are the only points that we know, how are we going to connect this graph? I don't know what this graph is going to look like. But I think what could help us is looking back at the function and trying to figure out, like, what is that? What are we looking at? What is this f of x? Take a look at that graph that they gave us on the left. What do you think we're looking at? You know all of the functions at this point, basically. You can talk really specific. You can talk more in general. What do you think f of x is? Yeah. Probably degree 4, right? What leading coefficient we got? The arrows are pointing down. Probably negative. We're probably looking at like negative x to the 4th plus some stuff. That's probably a pretty good guess. Now, could it be x to the 6th? Or x to the 8th? Or x to the 10th? Could be. Now, we don't really know a lot about those higher degree functions. Usually, with higher degree functions, we'll see more terms. Right? I don't know if you remember, but the maximum number of extrema is n minus 1. It's 1 less than the degree. So if this is degree 4, 1, 2, 3 extrema, so that's good. But it could be less than that. It could be degree 6 with only 3 terms. Usually, if we don't have n minus 1, there's like some flattening or some flexing or some weird stuff kind of happening away from the extrema. So I feel pretty good about this being negative x to the 4th. And so what kind of function family does that fall into? Polynomials. What do we know about polynomials? They're continuous. And what do we know about the style in which we graph them? They're smooth and round. And if that's true about our function, if our function that we're looking at is polynomial, let's say it's degree 4, what's the degree of our derivative? Take away 1, right? Rule for the power rule just says take away 1 from the exponent. So if our function's a polynomial, so is our derivative. Now, the thing we want to watch out for, we haven't talked about this, there are polynomials that at points might have a vertical tangent line. They can still be continuous, but what's the slope of a vertical line? Not 0, undefined. Which means that your function's derivative doesn't have to be continuous. But we don't have any of those, so I feel really good about trying to draw this like a polynomial as best I can. I'm going to connect it smooth and rounded as best I can. Give me like 30 seconds. I know the bell's going to ring. Because I got to talk about what's happening on the left and the right. And then we'll go. I just want to get to the same spot that period 2 did. What's happening here and what's happening here? Going down, but from left to right, this side is going up. This side is going down. This is going up so fast, which means its derivative is very positive. It's increasing quickly. Same thing, but here, oh, no. If this is negative x to the fourth plus some stuff, look what we've got. Negative x to the third plus some stuff. And of course, some constants in there too. But it matches and it looks so good. Okay, there's my 15 extra seconds. Have a great day. Nothing you got to do. Just come on back tomorrow and I'll see you. Thanks, everybody. Evelyn, don't forget your stuff under your desk. Miss Byrne, what's up? Yeah, that was perfect. Yeah. No, that was perfect. Thank you.
Yeah.
That's awesome.
Adios.
See ya.
Oh, there's the last one out here. Hi,
Because you're getting organized, you're
I
taking your
know.
time.
I have just too much stuff.
I know. You and me both. See ya.